Uh, let's start today. And as a first speaker, we have Javi Yeste. He studied his degree here in Valencia, also his master degree in photonics. And today he is going to, and now he's doing his PhD here in Valencia as well. And today he is going to talk about one part of his PhD work, which is about metal oxides for applications in infrared, plasmonics, and optoelectronic devices.
Thank you. Can you hear me well? Yes. Great. So, as he said, I'm going to show you a part of my work, but I will try to present it as an entire project, because I only work in a part of it, which will be the growth of the material. But this material is grown because we wanted to have some applications, so I will talk about these applications and why we think this is interesting. So, okay. So I divided the talk in 3 parts. First, we will speak a bit about photo detection, which is the application we want to tackle. Then we will talk about the material choice and how are we going to do it, and then a little bit of how we actually do it, and then some concluding remarks. Do you hear me well, or when it's a bit difficult? Okay, you were right. So if I want to start with some applications of these detectors, which detecting the infrared light, which is in the lower part of the visible, if you go to lower frequencies. So, for example, it has applications in astronomy because they look at the universe in the whole spectrum, because you can see different things. So the infrared is very important in this realm. Also, it can be used in spectroscopy because some molecules have vibrational modes that are excited with infrared light. So if we excite these modes, we can know which molecule are we looking at. And finally, finally of these 3, because there are many more, but you can do thermal images, which are used in medicine, for example. So how do these detectors work? Mainly there are 2 kinds. One of them are the thermal detectors, which are cheaper, but they have low efficiency and they require a high detection volume. And they work like this. We have our detector, which would be this here, which initially is cold. But when we make infrared photons inside in our material, they will scatter, and all this energy will be transferred to the material heating it. So by measuring the temperature of our material, we will know how much light we got into it. And on the other hand, we have photodetectors, which have higher efficiency and lower detection volume. And this work we need a system with discrete energy modes. Something like this. These are energy modes, and the electrons can be put in these levels. So what we will do is put some light into it, and what this will provoke is these electrons to be transferred from one level to another one, or even can be free from these levels here. When these electrons are free, we can put a voltage and measure the intensity we have. This is something similar to the Bohr atom, which you might know, in which we have some orbitals with defined energy, and with photons we can make some transitions. But for detection, we can use an atom. So what we will do is a narrow bandgap semiconductor. If the bandgap of our semiconductor is very, very narrow, we will have energies of that of the infrared. But what we are going to use are quantum well infrared photodetectors, in which what we do is we stack layers of different materials with different bandgap. So we do these well-like structures, and in these wells it happens that we have these discrete modes, and the transitions between these modes are similar to the infrared energy light, and have the same energy as infrared light. Okay, so we are going to focus on the photodetectors because they have better efficiency, but still they have some problems, and this happens because the infrared light is very low energy. So some thermal fluctuations in our material can trigger these same transitions. So we will have a very noisy signal, because some of it will be triggered by the photons and some of it will be triggered by some thermal fluctuations. So in order to address that, we have two options. One of it is to cool our material to cryogenic temperatures, and with that the thermal fluctuations are blocked. So what happens with this is that it increases the size of the size and the price of the detector because it needs an external system, and yeah, this is more expensive to make. And another option is to reduce the volume of detection, because if we have way less volume, we will have way less spots in which we can trigger these thermal fluctuations. So, and also this will reduce the cost and the size because we will need less material to make it work. Okay, so reducing the volume seems like the best idea, but this is not something we can do without adding nothing to the detector, because I've put some silly analogy here. So imagine we have this shower head dropping water, and initially this is our detector. So all the water feeds in the detector, but since it's very, very big, we will have a lot of noise. So we decide we need a smaller detector. But what happens if we do this? That only this part of the water, or in our case the light, will be detected by your material. So what can we do in order to feed all of this water into our detector? So we can use a funnel. With this, we can get all the benefits of getting all the light and the benefits of having a small detector. But obviously, we are not going to put a funnel in a photodetector, so we have to find an alternative. And we think that a very good alternative would be plasmonics, which I don't know if you are familiar with, but I will give some very simple explanation of what they are. I will read this. A plasmon is the collective oscillation of free electrons near the interface between a material with metallic behavior and a dielectric. So this means if we have some material which is metallic, which means that we have free electrons in it, and some material which is a dielectric with no free electrons, what we can do is we can make light inside in it, and these electrons will begin to oscillate, and they will generate a new field that will be way more intense and will be confined in a very small region. So if the infrared has like 2 micrometers wavelength, this region can be of the order of 100 nanometers. So with that, we can make the detector smaller. And we have two kinds of plasmons. One of them are localized and one of them are traveling modes. In the localized modes, what we need is a small region in which the electrons will oscillate and generate this new field, like you can see here. And if our particle is spherical, we have no problem, and we only have one mode, because it's symmetric. It doesn't depend on in which direction it oscillates, because they always see the same thing. But what happens if we have an hemisphere, so a cut sphere? We have two different ways of oscillating the electrons. So if the light is polarized this way, the electrons will oscillate parallel to the substrate. And if the light is polarized transverse to the substrate, they will oscillate like this. So these two plasmons will be excited at different frequencies because they are different. And we have what we call the high energy mode and the low energy mode. And these two will have different properties, which we will see later on. And we also have the traveling modes, and in which what we have is that the electrons in the interface are excited and generate this new field, but this can propagate in the plane of the interface. Using this kind of plasmons for our applications has some advantages and disadvantages. The disadvantage is that we need something else to excite these plasmons. With these particles, we can excite them with direct light. But here we will need to use a prism with higher refractive index or make some pattern with lithography. And this is the disadvantage, is that it's more work to do. But the good thing is that we can design these patterns to change the properties of our material. So okay, here I've put some drawings of how the different plasmons would affect the detection. So here we have the bare detection material, in which the light can be detected or can cross the material without interacting with it. And here we have the initial infrared photodetection, which transforms into a new field, which is confined in a small region, or here confined in a small region that travels through the interface. So what we can do in this case is to reduce the volume without problems. Okay, so now we know what we want to do. but we need to find which material would be optimum for this task. And before I showed you that the plasma frequency depends on some parameters, but mainly it depends on the density of free electrons. So typically metals are used for plasmonics, but since they have a lot of free electrons, the plasma frequency lays in the ultraviolet or the visible. So since we want to use our detectors for the infrared, we will need some material with a smaller quantity of free electrons. So with metals, we have a lot because the valence band and the conduction bands overlap, so all of these electrons can move freely. But in a semiconductor, since we have a band gap, these electrons are confined, and only the ones that lay in the conduction band will be able to move. So if we count the electrons of these two materials, we will see that in a metal we have something like 10 to the 28, while in the semiconductor we will have 10 to the 21 or something like that. So we go from having the plasma frequency in the ultraviolet to the infrared, which is what we want. So cool. We want to grow a semiconductor, and we have seen that a very good material is cadmium oxide, because it has an intrinsic carrier density of 10 to the 20, and these are some properties of the material that, well, this is the lattice parameters is the distance between atoms. This is the permittivity, which is very good for plasmonics. I won't explain why. And the expansion coefficient, this is not very important. So cadmium oxide would be a very good material, but we have seen that if we we alloy it with zinc, we have some advantages, and we can do this alloy because the zinc and the cadmium are very similar materials. And if we put something in our material, we have demonstrated that we can have a higher mobility, and we can increase the free electron density. And with that, what we can do is we can tune the range of frequencies in which our detector can work. Okay. So yeah, until now I haven't talked about what a crystal is. Some of you might know, but it's very important for the next part of the presentation. And as I've written here, a crystalline solid is a highly ordered solid formed by a regular repetition of its building blocks in a three-dimensional periodic array. This being periodic is very important. If it's not periodic, it's not a crystal. So I've put here the different unit cells that we can have, and here an image of a crystal, in which we can see it has this hexagonal shape. And this happens because it's formed by this kind of cell stacked in a three-dimensional array. And another important concept is the epitaxy, which we call epitaxy the process in which a new material is deposited on a substrate, and we try to make the new crystal follow the crystal structure of the substrate. Okay? So here I've put a TEM image in which you can see these white dots are atoms. So I don't know if it's very clear to see, but the atoms in the substrate are ordered in the same way as the atoms in the layer we've grown. So yeah, now I'm going to show a bit how an epitaxial growth would happen, and this is a very famous image for the crystal growers. And imagine we have this kind of structure with some steps, and we have some atoms that get to this surface. Okay, so this atom here would close one bond with the surface, but would leave 5 more free. So this is not energetically favorable. So what would be more favorable? So going here, you would close 2 bonds, one with the wall and one with the surface, and here you would close 3. And even if you have a hole in your layer, you would close 5. So if we have this space available, typically the atom will end up here. So imagine this here is our substrate. So the first atom has to go somewhere. So let's say here. And the next one will try to come here because it closes 2 atoms. And what would happen if another one came here? It would leave 3 atoms free. 3 bonds free, sorry. So this is not energetically favorable, so it's less likely to happen. So we don't want this. The next one will come here, and here, and here, until we finish 1 layer. And after this, again, the next layer. And with this, we have this kind of single crystal layer with no defects, because the lattice parameter of the crystal and that of the substrate are the same. But what happens if the crystal and the substrate have different lattice parameters? So we can't accommodate these atoms to those of the substrate. So what we will have is that they are strained. So for example, we can't fit an atom here because we have no more in the substrate. So they will begin to grow like islands. And they will grow islands like this. And also, if we look at the free bonds we leave, in this region we have a lot of free bonds, which are not in this case. So these structures are not energetically favorable. So what this will try to do is to reduce the surface in which we have the free bonds and increase the volume where we have the bonds all closed. So the shape that has the lowest surface to volume ratio is the sphere. So that's why the water droplets are spherical. So we can expect in a mismatched lattice to have structures like this. And if you remember, I talked about how hemispheres are good for plasmonics because they have two different modes that we can use. So yeah, here I've put some images of cadmium oxide grown on sapphire, which has the same lattice parameter as cadmium oxide and sapphire share the same lattice parameter, and one with gallium arsenide. This stopped working. Yeah, this doesn't work. So, can I? No. Okay. So. Yeah. So here we have the same lattice parameter, so it grows like I told you. And here we have a mismatch, so they grow like separate islands, and when they find each other, they have no option but to grow vertically, and we have this kind of structure here. And for a short deposition time, here we can see how the islands are, not the islands, the layers are finding each other. And here we can see the hemispheres I was talking about before. Okay, so sapphire is very, very nice for growing cadmium oxide because of this, but it has no use in photodetection. So even though I would like to grow on sapphire, I have no option but to grow on gallium arsenide if we want it to be useful for photodetection. So yeah, now we know what we want to do. We're going to grow cadmium oxide and cadmium zinc oxide crystals on top of gallium arsenide substrates, and we need to find how we do this. So here in our labs we have an MOCVD system, which stands for metal organic chemical vapor deposition. Metal organic are these nasty molecules in which we have some metal and some hydrogens and carbons, which honestly I don't, maybe I should, but I don't care about them. So what we have is, I will explain it from first to the end. So we have a nitrogen bottle, which we can change it with argon or helium, something that doesn't interact with our material. So we open this bottle and we have gas going through the pipes, and it will go until the bubbler. The bubbler is where we store the precursor. So here we put the gas into the liquid phase and it will make bubbles. That's why it's called bubbler. And they will go to the surface, explode, and we will have this gas, but filled with these molecules here. So this will go again through the pipes until it reaches the reactor. Okay, so the reactor, what happens here? So we have a constant flux of gas, so the molecules will go this way. And what we have is a susceptor, which is called this piece, but it's just a piece of graphite, which is heated by a radio frequency system. So this generates an oscillating magnetic field and generates some current in here, and by Joule effect, this heats up. So when these molecules go and find this hot piece of material, they will pyrolyze. And this means that because it's very hot, these bonds between the molecules will break. So we will have free zinc, for example. We have different bubblers. So in this case, zinc. And all of these will be, since it can go into the crystal, it will be freed. It will go through some filters and left to the atmosphere. And also I put this remote control here because all the system is, you can control it with a console. Okay, so if this was my system, my work would be probably done because this is very easy to manipulate, but my system, it looks more like this with all the pipes and all the valves and all the problems it can give you. And yeah, we can come back to here and see that this pipe here is not just a pipe, is more like this panel. The bubblers is not just a rectangle, the bubblers would be this thing here, and they are stored in thermal baths because we have to control very well the temperature at which they are. These are the reactors. We have two. We have two for growing different materials. In one reactor, we only grow cadmium oxide because these systems have a very good memory, and if you put something else, the next crystals you grow will have this material even if you don't want it. With the radio frequency system here, the remote control is more something like this, and well, to be realistic, the time in Valencia is not always this good. Yesterday morning it was more like this, for example. So yeah, and now we have everything, we know what we want to do, and now what's left is to do it. So I want to talk a bit about how the crystal grower has to operate. And this is, we have our system in which we have a lot of growth parameters that we can control. And the idea is to do series of experiments. So for example, we want to change temperature to see how this affects to our growth. So we will change temperature, and after doing this, we will go and characterize our sample. So when we know what are the effects, the temperature, we can go on and try a different parameter. So we will do series of experiments and try to approach the final result we want to get. Here I've put some parameters we can change in our MOCVD, which are not all of them, there are even more. So yeah, when you want to get a certain morphology, it's very difficult because you have to understand every one of these parameters and how they affect the growth. And yeah, I put here some characterization techniques, which we have electron microscopy which give us the images I showed you before. X-ray diffraction to see the structure of our crystal, electron diffraction, to ADX to see the composition, and optical and electrical measurements as well. So yeah, and to finish, I've put some examples of work I've done here, which is for regarding cadmium zinc oxide nanoparticles on gallium arsenide. And at first, what we tried to do was to, we did it. We changed the temperature to see how this affects the growth. So we can see that here we have very little particles and that they are very big. Very little, no. We have very low density of particles. And they are very big. And as we increase the temperature, we can see that we get more and more particles and they reduce the volume. So if we want to use it for increasing the detectivity of photodetectors, we can have this because the substrate is almost as it was before. So we would prefer something like this, in which most of the substrate is covered. So yeah, we know that we won't work with these two temperatures, but any of these three seems similar. So in this range, we can change it, and there is no problem. So after that, we wanted to see how the amount of material we put in affects. So we've done some experiments by changing the flows of the different precursors and putting the same amount of material. So if we put a lot of material at once, the supersaturation will be higher. This is like when you are having a bath and the water condensates on the mirror. This happens because there is a lot of vapor of water. So it will be something similar here. But we have seen that apart from this experiment here, in which we have higher deposition, these two look quite similar. So we decided to go on with this. And when we have the temperature and the flows decided, we've done a series of experiments with increasing the deposition time. So we can see that for 90 seconds, we have mainly isolated nanoparticles. And when we increase the deposition time, we go from this until we have a very nasty layer of particles that are glued together. So, and another thing that I found interesting is that the position in which you do the growth affects a lot the result, because the temperature here and here might differ, because the amount of material that gets here. Okay, this is something like the reactor, so front is the part closer to the entry of the material. So here we will have more material than here because the susceptor and the substrate will absorb it. So, and the hydrodynamic conditions here are very different from here. So in the same experiment for a 2-minute growth, we got this in the front position and this in the back position. And we did the optical measurements, and these particles are too small for exciting the plasmon. So we kept on studying this, but we never stopped doing growths in this position. So afterwards, we decided we wanted to do thin films, and here this sample was very, very useful, because if we have more particles, when they grow, they will find each other first, earlier. So we go from having films nasty like this, which are like a lot of mountains, to having something that is very thin. So this is an example of how studying your system, even if it doesn't look like it will have applications, is very important, because later on you can use these results you've obtained before. And I've put here finally the optical characterization of these samples. We have 4 samples in which the surface coverage increases, and here we have a lot of coalescence of the particles. And here I show the transmittance spectra of these samples. So we can see that in these 2 we have a part in which the light doesn't go through the substrate, and this happens because we are exciting the 2 plasmonic modes I was talking about before. We have the low energy and the high energy one. In these cases, the low energy one is the one in which the electrons oscillate parallel to the substrate. So we have these modes in these 2 samples, but when they begin to find each other, we see that the low energy mode begins to deteriorate. And this happens because since we are putting particles next to each other, we are losing the lateral confinement. So we can't excite plasmons if the region is not small enough. So these samples here, the vertical confinement is still there, so we have the high energy mode, but the low energy mode ends up disappearing. And this is very bad, because we've done some simulations of how the field that these plasmons generate are, and we can see that in the low energy mode, the field penetrates the substrate, while in the high energy mode, the field stays inside the particle. So if we want it to go through the substrate, this mode is very bad, because we will lose a lot of energy. And also the field here is way stronger than here, because if you look at the scale, here black is 15, so 15 times more intense, and here is 100. So the field in the vertices of the hemisphere is 100 more intense than the light we radiate with. And here I've put some simulations of how the absorbance of the substrate would increase by putting these arrays of particles that we can grow, and which you can see something significant. And that's all for my work, but I wanted to talk about a bit crystal growth in general, because this is just the technique I use and the material I grow. But there are lots of different kinds of materials you can grow, and lots of different techniques. So for example, here I've put some 2 simple techniques for growing volume materials. So this is something like this, way bigger than the other things, which I don't know if I said, but this is nanometer length. We don't have the scale? Yeah, this is 100 nanometers, and this is some centimeters. So growing this with MOCVD would be an idiocy. This makes no sense. So we have, for example, this method, which is called the Bridgman method, and it's just a furnace in which we will put our material in an ampoule, we will melt it, and we will make a temperature gradient with different heat sources, and we will make it go through these gradients, so it begins being liquid and it ends up being solid. And if we do it well, we can get a monocrystal, which has these nice properties. This is not mine, I get it from an article. And this technique always, I think it's very cool, because it's very simple. You just put a seed material, which is the same crystal you want to grow, but a small piece of it, and you put it into a bath of molten material. And the only thing they do is they pull this seed, and yeah, the molten material goes here because it's cooler, and it solidifies and makes crystals that are this big. And with that, they make silicon wafers, which are widely used in many applications. And these are some techniques in which you can do very small materials, as the MOCVD one. And I've ordered them from being very, very cheap, this would cost like 1,000 euros maybe, to something like this that would cost millions of euros. This is very simple also in theory, because what you do is you put some liquid with your material here, and it goes through a nozzle, which is like like what you use for cleaning the windows, just a spray. The substrate will be hot and the liquid will evaporate and the material will get here. This is PLD, which stands for pulsed laser deposition, and this is something similar than I explained before, but you attack the precursor with a laser, so you get the material from there by making a pulsed laser hit it. So a plasma is created here, so it will end up being deposited on your substrate. And this is MBE, molecular beam epitaxy, and here what you directly have is some cells, some effusion cells, in which you can shot beams of atoms, of pure atoms. So with this you have very high control of the material you grow. And here I've put some materials which are different, but this is something we've grown here with spray pyrolysis, and you can see it's very, very rough. This is some material grown with PLD, which is way more soft. And what you can see here is a TEM image of heterostructures grown with MB. So I don't know if you can see, but this is like 10 atoms thick. This is very, very, very thin, and they have very good control of its morphology. So yeah, these are good because they are cheap. These are good because they grow very quality materials, very good quality materials. And yeah, these are just some of them. I've put this diagram here in which you can see that there are many more. We don't have everything here, also because this is from 50 years ago. So people keep on developing new methods. And yeah, and that's all. I wanted to say that this is, maybe you didn't know about crystal growth, which I didn't when I started with it. But it's a very, very big field in physics and also in chemistry and engineering. And yeah, lots of people working in it, so maybe if you are interested in it, you can try to look a bit more after it. So yeah, so that's it. Thank you. And if you have any questions, I'm happy to answer them.
Now we have time for questions, so if anyone has any question, please raise your hand. So I have one question. Well, is there any question here?
To the what? To the you know about it, right? But I mainly work on the growth. So this is not something I've done here. They do it in a group that works with us in Madrid. So yeah, I know that only the set direction of the field goes into the quantum wells and can be absorbed by the quantum wells. So here you can see with this. Here you can see these lines show the direction of the field in every point. So in the vertices, even with light that was not initially polarized in the set direction, it diverges. So some of it will have this Z component, and it can be absorbed by the quantum wells. I don't know if that answers your question. I'm not very familiar with this. I just have a general idea. But yeah, since if this has to be light polarized like this, so it will go here, and it wouldn't be taken by the quantum wells. But since it excites a plasmon here, it will generate this new field, which has this Z component and can be absorbed. And what this tells you is that if you use this light, initially you don't get any absorption because it doesn't have the Z component. But when you put the particles, then you begin to have this Z component, and they can be absorbed by the substrate.
Any other question? So these crystals, they are used for detectors, but what is the main use of these detectors in many areas, or it's very specific area?
Well, for almost everything. Well, it's in the first slide, but yeah. For example, in medicine they can be used because I think I don't want to say something silly, but I know there are you can have some problems which give you a higher temperature. So if you can detect that, you can know you have these problems. I don't want to say which specific because I don't know. And yeah, for example, in astronomy, it's used because you want to look at the infrared spectrum of some star very far away, and they are used for that. And in chemistry, they use it for characterizing materials, and yeah, for lots of things. And for these cool images you have in video games when you put these thermal goggles and you see everything, how hot it is. Also for that.
I see. Thank you. Any other question? If not, let's thank again the speaker. ¿Nos escuchas? Okay.
Sí.
So our next speaker is Betsu Santamaria. She studied her physics degree in the University of Salamanca, and then she moved to Madrid in the Universitat Politécnica de Madrid, where she obtained her master's and her PhD. Now she's still working there, and apart from science, she is also an activist for women visibility in science, and we thank her participation in this school because she just had a baby 6 days ago. So thank you for giving this talk.
Okay, can I start? Yes.
Yeah, go ahead.
Okay, so thank you very much for the organization, for inviting me to talk today, especially to Martina Delgado, who is the person that I've been in touch with. Before going further, I would like to explain the logos I have put here, down here, because there are many logos, but they are all of them important for my job. So, as you said in my presentation during my introduction, I'm a professor in the engineering school in Universitat Politécnica de Madrid, which I dedicate most of my part of the day to teach, but I'm a member of the group of optics, photonics and biophotonics that is located in other town outside Madrid, but is also part of this university. And here is where I perform the rest of my research, and I spend the rest of my time. But also I'm part of the Optical Spanish Association, where we organize a lot of talks and informative talks about science and mostly about optical area. So as I said, I'm part of the group of optics, photonics and biophotonics, where I perform my doctoral thesis and I do part of my research. Right now, we are about 16 members from multiple areas. We have industrial engineering, people with degree in chemistry, telecommunications, physics, environmental science. There are also biologists and so on. And why we have people from all these areas? Because the multidisciplinarity is a must if we want to perform applied science. And this is how we can cover all our research lines. In our group, we cover all the research lines, mostly based in light science. We fabricate photonics transducers, B cells for label-free biosensors that I will explain later on, packagings and kits. We also do optical characterization. We have several instruments, for instance, the Fourier transform infrared spectrometer, an ellipsometry, several point-of-care devices that we have developed. And we also take care of the micro and nanofluidics that we also fabricate and develop in our lab. Lastly, we care about the surface biofunctionalization of the optical transducer that we have fabricated, and we perform this biofunctionalization to develop several bio applications to clinical detection, environmental detection, and chemical detection. For instance, we can detect diagnosis of several diseases or chemical components, pathogens, contaminations, and also perform analysis, chemical analysis of several fluids, for instance, the petrol, the gas. Our goal is to develop a cost-effective detection that can be included in the market. So if there is a word that summarizes all our research, is the biosensor. What is a biosensor? It is a device that can transduce an biological interaction into a measurable signal. How does it do it? This optical interaction that could be, for instance, between a protein and antibody is transducer by a transducer, and this signal is collected by an electronics or optoelectronics devices, processes, and then displays gives you the results that can be understandable by anyone, not only by the scientist. So there are many classifications of these biosensors. We can classify them in function of this biological interaction or in function of this transducer. If we classify them in function of the biological interaction, in this case, in our case, the biological interaction that the sensor detects is the bioaffinity. It is the interaction that occurs between a biomarker, for instance, a protein, an antigen, and a bioreceptor that, in our case, usually is an antibody. This type of diagnoses are very, very reliable, since only a specific part of the antibody, the antigen binding, recognize a certain part of the antigen, the epitope. In function of what is detected by the biosensor, an indirect or indirect immunoassay is performed. If we are detecting the antibodies, we talk about this indirect immunoassay, and if we detect the antigen, we talk about direct. And the other classification that we perform is based in the transducer. More precisely, I would like to introduce you this innovative classification for optical transducer based in the complex index, refractive index variation. As you might know, the refractive index is composed by a real part and an imaginary part. So we can classify the transducer in those two parts. One based in this imaginary part, and the other one based in the real part. The most common and most popular sensors, biosensors, or assays based in the imaginary part are, ELISA and lateral flow. And if we base this classification in the real part, we can have this surface plasma resonance biosensors, optical fibers, and interferometers that are the ones that we use in our research lines. So this is the biosensor that we use, based in a Fabry-Perot interferometer biosensor. What we have is several layers of sensor, which spectra change in function of the layers of this interferometer. Thus, if a new layer, such proteins, are attached in this surface, the refractive spectra varies, and this variation can be related with the protein concentration and is the basis of the proposed biosensor. As a readout method, we usually use a standard and well-known technique in the science area, that is the Fourier transform spectrometer, which gives a reflected area from this Fabry-Perot biosensor in every step of the immunoassay. Thus, if the variation of this spectra is represented against the concentration of the detected biomaterial, a standard curve can be drawn. And what we are looking for now? Usually, biosensors are accompanied by point-of-care devices. The Fourier transfer interferometer that I mentioned, it is not a point-of-care device. As you might know, if people know, it's a huge instrument that needs a very stable environment, needs to be inside a lab with these optical specialized tables, no vibration, and the spectra that you obtain are in this kind of a spectra. So if you give this kind of data to a doctor, it could be very difficult for them to interpret the results. So what we are looking is to transfer this kind of readout into a point-of-care device. There are many point-of-care devices in the market. There are some point-of-care devices that perform very high performance, very sensitive, but they also are very time consuming, very, very expensive, and they need probably a high volume of samples. There are very, very simple point-of-care devices, as you might know, the lateral flow biosensor, for instance, the pregnancy test, or nowadays the COVID test that sounds everywhere. That they are very, very simple, low-cost technology. They can be used by the patient itself, but they have very low performance. Normally, they are a yes or no biosensor. They don't give you quantitative information, and they also need very high volume of sample. So looking at those point-of-care devices, these two point-of-care devices that we can find in the market, we want to provide an ideal point-of-care device that will be simple and cost-effective, very simple to use. It will be as a portable device to be in the point of need, to provide a quantitative results and near to the patient. As for example, it is the famous glucose detector. As I said, the FTIR, the Fourier transfer spectrometer, needs a very complex facilities, and it provides a very complex data. So in our group, we tried to transfer this kind of readout into this kind of readout that we call the increased relative optical power. If we transfer this kind of measurement into this one that only needs one laser to perform the readout and the photodetector, we can reduce the size of the device, and we can incorporate a software that provides you instantly the concentration of the biological material that you want to detect in a step of these strange curves to the doctors. This is a method that has been patented and also is based in the light. As you might know, the light has several components in several wavelengths that can be divided in several velocities. And it is very important the selection of the light that we are using into our biosensor. For this purpose, to synchronize the biosensor spectra that we obtain to our readout method, we use the lithography fabrication method. More precisely, the contact mass lithography method. This technique, I don't know if some of you know it or not, but is based in a wafer level. We perform it in a wafer level so we can fabricate several biosensors only in one step. We put a photosensitive resist and a mask. This photosensitive resist is sensitive only to a certain wavelength that we use to expose this resist only in the parts that the mask shows the light. So when the light is exposed, the geometry that we want to draw is drawn in the photoresist, but there are still some parts that they have not been exposed. These parts can be removed by a chemical etching, and thus we have the geometry that we want. We play with several architectures of the sensors. We play with photonic crystals that we can have this photonic bandgap as reflective spectra, and we also fabricate Fabry-Perot resonators, as I said before, that provides this kind of resonant peaks. If we combine these two techniques, we achieve finally this kind of a spectra where there is a photonic bandgap, but also this resonant peak that will be very easy to monitorize by our device. So in this sense, we increase our sensitivity. But also we play with the evanescence file. Since if we have only one of these resonant nanopillars, it will be this contribution in our evanescence file. But if we combine several nanopillars, we can have highest contribution in this evanescence file, so our sensitivity again will be increased. And that's how we patent our photonic biosensing cells, the B cells, that are composed, as you can see here in this same imaging, this photonic crystal, periodic lattice, and the intermediate resonant cavity. And the side of these sensors are comparing by 1 cent coin are such this small size. Imagine that we can perform a diagnosis in one of these tiny squares. It is true that the technological part we have under control, but to immobilize antibodies and proteins and so on in such small areas, we are still doing it. But what we do is to cover all one chip, all one biosensor by our reactives, and this is how we can have several replications in our data. So as I said, we can fabricate our sensors, we can fabricate and we have developed our point of care devices, and so we transfer this kind of signal into a very understandable signal by the doctors. And now what? Well, the second part that we research is the bioapplications. We have investigate into infectious disease. We have detect dengue, influenza A, rotavirus, and lastly the COVID-19 also. We have also work in a European project that detect contaminants in the seawaters. We have investigate in diagnosis of ophthalmological disease, the dry eye disease, for instance, and also systemic disease like Alzheimer. And our last project that has finished just this year was alert screening project that was covering the detection of 200 allergens. How we do perform this diagnosis? I will be very simple providing you this explanation because we are not biologists, but I think that you will be able to understand. For instance, I will base the explanation in the COVID-19 disease because this is one disease that all we have in mind. If we take a saliva sample, a person who is negative in COVID will have the saliva and all the proteins that the saliva has in this sample, but not antibodies against this disease. However, a person who has been positive in COVID will have several antibodies. In this case, because we want to detect these antibodies, the antibodies will be our biomarkers. So, which one is our bioreceptor in this case? The COVID virus. Thus, we immobilize this virus that is not active, fortunately for us, in our sensors, in our sensor surface, and we incubate those samples. Those samples, we provide them 13 minutes to produce the biological interaction between the virus proteins and the antibodies, and later on we wash them to remove all the interference of the rest of the proteins that are included in the saliva. Later on, what we have is our point of care device, and by applying light, laser light, we can communicate or we can see what happens on this surface, and the point of care device provide us the results, very simple results. In function of the software that we have included in this device, we can see if there are several proteins with higher level, lowest layers. If we include the calibration curve, we can provide also the concentration of these biomarkers and so on. The advantages of our optical biosensor and point of care devices, comparing what we have in the market that they are using ELISA tests or PCR or lateral flows, we can say that our point of care device is not using such amount of reactive, for instance. Also, the ELISA is very, very, very expensive. It needs a lot of time, needs specialized people to perform the test. You need to collect the sample, drive it into a specialized clinic, so the time goes increasing and so on. And our tests that are very, very small ones can provide more or less the same amount of diagnosis of the ELISA test just with 1 or 1.5 microliter sample. We nowadays we are performing in one kit the diagnosis of 7 patients. We have 65 diagnoses to perform, but we want to have several replicas to be sure of our data. So we are performing the diagnosis of 7 patients. Imagine the volume that we are using. It is the size of a point of a pen. So it's very, very low volume, which is not only good for the patient because you not need to take or remove a lot of sample from him, but also for the economical issues because we are using very, very low volume of reactives. And the results have been already published in Sensor and Actuators. So thank you very much again for the organization to provide me this opportunity to show our research, and I will be very happy to answer your questions if there are some.
Thank you very much for the very nice talk. Does anyone have any question? I have one question of my own. that you said that biosensors can be of two types at the beginning, maybe, if I understand correctly. You can have antibodies to detect the disease, or you can have the disease to detect the antibodies, right?
Yes, this is what I name called indirect or direct diagnosis, right?
Mm-hmm.
We can perform direct, I want to find it.
It was at the beginning. Yeah.
We can have, for instance, if we are talking about the COVID, right? We can have the antibodies and blood sample, for instance, that detects directly the virus, or we can have proteins of the virus and we can detect the antibodies that our body has generated against this virus. So we are not directly detecting the disease, we are detecting it indirectly. Just by
And my question is, how do you produce these antibodies or the disease for the detector? You produce them synthetically, or you obtain directly from biological systems?
The antibodies are the ones that you have in your body. If you
I mean the ones you use in the detector.
If we are detecting the direct one, right? There are commercially a lot of antibodies. They are already selling them. A lot of pharmas. But which is more curious is how we produce the protein, not the antibodies. The protein is produced in one of our research centers of the Polytechnical University and is produced in plants.
Okay.
So it's more curious.
And the device you were talking about that you or your group designed can use both direct and indirect methods?
Yes.
Or?
Yes, it is very versatile. I don't know if this is the word, but this is one of the advantages of the device, that is not only for this kind of interactions. We are now working with cells, and we are working in a lot of several bio applications. So this is the advantage of our system.
So it is a multi-purpose for different diseases. You have a very defined method to detect, and yeah, okay.
This is why we developed so fast the COVID diagnosis, because we have a lot of work done before with other diseases.
Okay, thank you for the answers. Any other question? Yes.
Thanks for your talk. I wanted to know, in your case, you say that for this method you need a translator to translate like the sample to an input. I maybe didn't understand well, but in your case was the optical one, the laser. There are other types of like translators to get the information from the receptors and the proteins to a signal transducer.
Okay, if I understood, because I have not listened very properly.
Sorry.
Is you are talking about other techniques of translate the biological interaction into a measurable signal, right?
Yes. Yes. Right.
Okay. Yes. We have a base transduction in optical signal, but there are also electrochemical signal that base the signal in electrical properties, or nanomechanicals, or piezoelectricals, for instance. So you can have several transducers. For instance, the glucose detector is electrochemical one. It's based in the electrochemical signal.
Thanks.
Any other question? If not, let's thank again the speaker.
Okay, thank you.
Thank you very much. So now we have the break, and you can wait outside for it, and that's it.